This is going to be a video all about magnets and electromagnetism, and I'm going to include the start of it and how to get around this area of the database. So this is just the code. It tells you what related topics there are to this topic here. It tells you how many resources there are and how many subtopics. If we scroll down, we can see the 8 subtopics that it's referring to. And if we keep scrolling down, you'll see all the resources. And these resources can be searched via different, well, first of all, you can just do a search here and type in whatever you want. So we've got DC motor there. If we just type in motor, all the things to do with the motor effect, all to do with motors, come up there within this topic. But then that was only simulations. So you got all, when you click on simulations, you got all the different other types of views, including, of course, all resources. So if we just click on all resources, then you've got answers, questions, and so on. Some of them don't have an image, but you'll be able to see here what type of resource it is, what level it is, and how it relates to other what subtopic it is, basically. So you can load a 50 more down there. Down at the bottom, you've got another list of resources, which is associated with related topics. So if you remember, the related topics were these ones up here. So it should have resources associated with that, so long as I've finished connecting them all. So I'll just pause the video now, and I'll get some resources that we can have a little play with. Okay, so maybe a good one to get started is the field lines. If we look at some of the field lines we've got, we've drawn field lines before, but this one, let me just show you. Click on this link here. This one shows you what it looks like in 3D, just so we can visualize that. Looks like you can move it around as well. It's pretty cool. These are obviously not how you would normally draw field lines, but these are iron filings, if they're able to sort of float in space, I suppose. So that's pretty cool, just to help you visualize that. We can also have a look at this one. I keep clicking, sorry, click on this thing down here. So this demonstrates what the field lines mean in terms of what the field lines actually mean when you draw them. And it means that if you were to place little tiny these loads of compasses around it, this is how they would arrange themselves. And a compass is nothing more than just a tiny little magnet that is able to freely move. So usually, quite often, what it will have is a tiny magnet floating on some water or liquid, and then covered in glass. Or sometimes it will just be balanced delicately, so it's able to spin quite freely. And you can see the north pole of these little magnets are pointing towards the south pole, of course, and away from the north pole. So whenever you draw these field lines, you would essentially draw them joining up, and the arrow would represent the direction the north pole would be pointing towards. What else do we have down here? So I'll just briefly introduce the ideas before going on to the slightly harder stuff. It's worth mentioning this one here, which a lot of people get very confused with. Why isn't my mouse visible? That's interesting. Okay, sorry about that. Didn't know why the mouse just stopped being visible. Any case, so I'll just change this as well. Right, and we want that to be. Oh, I don't know. Okay, so. The other thing I was going to show was this thing down here. Yes, whoops, I want to click on the link. So I'll just load that up. So again, so far it's just nothing new, but so you can see that when I point this down here, then the North Pole points to the South Pole, South Pole points to the North Pole. But look what happens if I click on Show Planet Earth. Now, the North, we think of the North Pole Well, this is the North Pole when we point our compass towards it. Um, when we point our compass towards it, then the North Pole of our compass, which is just the magnetic North Pole of the little magnet inside the compass, is pointing to what we call the North Pole of our planet. But our planet, the reason why this works is because our planet is one giant magnet as well, and that's due to its iron core, that it's able to have a certain amount of movement, and the atoms arrange themselves in a way that makes them magnetic, to overly simplify. And as you can see from this diagram, the North Pole of our planet is actually the magnetic South Pole, and vice versa. So this causes a lot of confusion for people, including teachers. I think when I first started teaching, I stumbled across this, and it was quite surprising. So the magnetic the North Pole of the compass really is the magnetic North Pole, whereas what it's pointing towards is the Earth's magnetic South Pole, although we call it the geographical North Pole because that's where my North Pole of my compass points. Okay, so that's that one. We can if you've got access to this, you can play around with these yourself. Next thing I want to look at is the right-hand rule. So we've got a few things to look that demonstrate this. You can see these right-hand rule things here, and it tells you the topic just there. I think those are the only ones. Let's have a look at this one. So again, click on the link to open up the simulation. And again, we've got the compasses arranged. So this is demonstrating that we have there is a magnetic field that gathers around a wire. If I click on right-hand rule, we can actually demonstrate how the rule is used. So essentially, what it's not showing here is the direction. Current direction switching. Oh, I see. So what it's not demonstrating is that the current is going that direction. The thumb is pointing to where the current is flowing. So if you know where the current is flowing, then if you arrange your hand in that way, the tips of your fingers represent the end of the arrow, and you can see therefore it tells you the field is flowing that way. So your fingers represent the magnetic field, and your thumb represents the current. And so you can move it around like that, and you'll be able to see how that arranges itself. So let's say that you knew where the magnetic field was pointing. The arrangement of the magnetic field, you'd be able to work out the current, or if you knew where the current was, you'd be able to work out the magnetic field. So there's a couple of simulations that demonstrate that. I don't know how. Oh, this is turning off again. Great. I don't know why it keeps doing that. Right, so let's have a quick look at the other one. Actually, I'm not going to look at the other one. The other one is going to be fairly similar. You can have a play with it yourself. I've introduced the principle. Let's have a look at some other things down here. So we've got, maybe we can have a look at a speaker. We'll see how speakers work. Speakers are quite clever. There's also a quite a good thing on electric bells, but I haven't managed to find a simulation for electric bells. So we'll have a look with speakers first. So the way that speakers work is you have a current that's set. You have an alternating current that represents the frequency of the sound, and obviously the frequency of the sound is changing. And so what happens is we have an electric. So I haven't introduced electromagnets yet, but an electromagnet is essentially when we use the magnetic field of a wire that I demonstrated a moment ago, and you can amplify it by wrapping it around in a coil, and that then produces a magnetic field similar to a bar magnet. We've got bar magnets here as well. So if we have the current pointing one direction, you might have the North Pole on one end, the South Pole on the other end, and then it might be either repelled or attracted depending on how that's arranged to these magnets. And then when the current flips, it does the opposite. So if it's attracted 1 minute, and then the current flips, then it's now repelled. So this causes this coil to be pushed out, attracted back in, and go back and forth. And the frequency at which it does that is based on the frequency of the alternating current that is supplied from your phone in this case. So, and that produces a frequency of sound waves. So, because what this does then is it compresses the air and then stretches the air out, producing compression and rarefaction. So this is obviously linking with sound and sound waves topic. And yeah, so I won't go into that too much detail because I'll be talking more about waves and sound then. This is quite cool. You can see the would be better if I could slow it down, but I can't. But you can just about make out that the arrows are changing direction. The current is changing direction, and this is causing the coil to be attracted or repelled by greater or smaller forces. The size of the arrow represents the size of the current, and that's causing the coil to be repelled or attracted to these magnets here. And it's a bit confusing because it looks like the magnets are up there, and so why is it being attracted towards the left? Best thing to think about though is that this sort of pink coloured thing, I presume, would be metal, and so it would conduct the magnetic field would pass through this metal, and because we've got magnets either side, then the sideways forces would cancel out, and so it would be attracted to the metal here. I hope that makes sense. So the speakers are pretty cool. One of the things you need to know about with magnetism is flux. So let's open up this one here, and this is demonstrating flux. So flux is just another word for magnetic fields, basically. You use the word flux more in A-level physics, but it does come up in GCSE physics as well. So if we're so the field lines we can represent as these arrows. If I press start, they actually move through, and you can when we're using things like what I'm going to demonstrate in a moment, the motor effect or the generator effect, or otherwise known as electromagnetic induction. What we're doing is we're cutting those field lines. So at the moment, what's happening is the field lines are being cut to an extent. So I don't know if we can demonstrate this. If I rotate it though, they're no longer cut through it because it's taking it at a glance. Okay. So you can see at this stage that the field lines are able to, if you imagine these moving, it's not really what happens, but we can imagine these movement. Actually, it wouldn't, the coil or this strip of metal, this square of metal that we've got here, wouldn't cut. They'd be able to avoid it completely. So the flux is 0 meters cubed per second. Don't worry too much about the unit. This is probably quite an advanced simulation, but it demonstrates that it helps you to visualize how we're cutting through these flux. So I can turn off that. And anyway, let's find something a bit more familiar to GCSE. Okay, so Faraday discovered something quite strange. He's a scientist from way back when, and he noticed that if he had a coil of wire, and we know already that a coil of wire produces a magnetic field, but maybe he didn't know this at the time. My history knowledge on this is not very strong, but what he noticed that when he got a magnet and he put it through this coil, the light bulb lit up. If he put it through and then it stayed still, there was no light wave. No lights were no light was produced, or no electric current was produced. So it was the movement that was key. If the more movement there was, the more current was produced. So the faster he moved it, the more current there was. So you can play around with these kind of things. You can change the loop area to see how that affects things. I won't go into too much detail. You can play around with that. See what happens if you increase the number of loops. You can measure the current with an ammeter rather than just using, oh, that's a voltmeter, sorry, rather than just using a light bulb. You can measure the strength of the magnetic field, which is basically this top number here. Those of you who do A-level will probably understand what these numbers mean. You can use a compass to see how that affects things. But what the main point is that when you move a magnet through a loop of wire, then it produces a voltage or an electric current. And we're going to go one way. It's difficult to really see, but when I do it one way, you get a current going, voltage going one way, or current going one way, and when you do it the other way, it goes the opposite direction. So, and we know from what we're looking at with flux before, I showed you in the previous animation, that what's happening is I'm cutting the field lines or the flux. I'm cutting the flux using this loop of wire. So I'm using movement and magnetism to produce electricity here. And this is those three words: movement or force, magnetism, and electricity or current. That's what really electromagnetism is all about. So I'm using magnetism and movement to produce electricity. In this case, this is electromagnetic induction. Faraday discovered this effect, or this is called the Faraday effect, this one. And then it can be applied, that's an electromagnet actually. It can be applied to something like a generator. So if I actually, so this represents a hydroelectric power plant essentially. If I get water falling through this by turning this tap, this spins around, and we have a magnetic current setup. Notice how also that it's an AC current. This is why your main supply of electricity is AC, because the magnet, at one point we got the south pole moving through it, then they got the north pole moving through it, then the south pole, and it switches back and forth. And that's why we have this, the opposing magnetic field here changes back and forth. So that's why we have an alternating current there. So that's and this you can call electromagnetic induction or the generator effect. And there, I'll talk a little bit more about generators in a moment. In a nutshell, generators can be separated into two different types: alternators and dynamos. Alternators produce alternating current, and dynamos produce direct current. Now, they don't produce direct current in the way that we normally think of. Like if I were to, I can't draw on this screen unfortunately at the moment, but if I would, I might be able to. Let's see. Can be a bit temperamental, but I'll talk a little bit more about this later on. But so if we imagine that being time against current, symbol I, an alternating current we know looks like this, and the direct current looks like this. Well, a dynamo doesn't produce a current that looks like that flat line, but it produces a current that looks like this. So if I've got time in this video, I'll explain why that is. That's a bit more complex, but the regular alternator type of generator will produce this alternating current. This flat line is what you'd get from like a chemical battery or a battery anyway. And then the dynamo would produce this kind of current. So we'll try to find out why that is in a moment. We can also play around with a transformer. I won't go into transformers straight away just yet, but because it's not the direct, I'll be running out of time pretty soon. But here's an electromagnet. So we can change the voltage, and let's get a field meter to measure the field. Make sure we can see 30.11 at the moment. If I move it away, obviously the field is lesser. But let's keep it in one spot and reduce the amount of loops on the thing, and it goes down. No surprise there. If I reduce the voltage, it goes down. What about if I go backwards? Well, this is actually, even for GCSE students, you might find this useful. I've BX, X is means that it's horizontal. So horizontally, the magnetic field is about the same as the total magnetic field at the moment, and that's because I've got it at a horizontal position from here to here. If I move it up slightly, we should get the. If I can get it just right, I can get by to be 0, but I can't quite get it. Never mind. So this one here is always going to give you a positive number. I think. Let's just double check that. Yeah. Whereas the BX will give you a negative number if it goes one way and a positive number if it goes the other way. And that can be understood using this compass. And then flip it around. The thing points to the direction. So that's electromagnets. Right. Let's see if we can do motor effect. What's the best? We've got a few different things. Oh, this is. Oh no, that's a motor. That's not an alternator, unfortunately. Let's see if I can find. This one would be quite a good one to do. So it's called the Lorentz force, but also known as the motor effect. I don't think you use the word Lorentz force in GCSE. So this is the motor effect basically, and you use Fleming's left-hand rule to work it out. So I'm not sure if we've got Fleming's left-hand. Okay, all right. So what we notice is that when you place a current in a magnetic field, so we've got a magnetic field there. Forget about this. This is using a different kind of rule. It's actually his right hand, but he's using the right hand to get the same answer as you would do with Fleming's left-hand rule. But you don't use this rule that we've got in the diagram at GCSE. So although it could give you the same answer, we'll forget about that for now. I don't know. I wish I could turn it off, but I just want to demonstrate the idea briefly. So we've got a magnetic field pointing up, north to south. The current is going that direction. And what would happen if I were to play this animation, if we did this in real life, is the loop would come towards it. It would actually move. So essentially, the motor effect is the effect that if I place a current carrying wire in a magnetic field, it would move. That's all that motor effect means. And we can apply this to make motors, of course, electric motors, and things that contain electric motors are anything at all that has any sort of spinning motion. That is electric. So hairdryer, washing machine, radio controlled car would obviously have a little electric motor in it. A fan, and vacuum cleaner, they all have spinning parts, and so it's going to be using the motor effect. So worth mentioning, I showed the speaker earlier on because I wanted to make sure that we realise that is not using the motor effect in that case. That's using alternating current to produce. To make an electromagnet flip direction. So it's still causing movement, but it's not using the motor effect. It's a different kind of effect there. So let's see if we can find another example. It would be quite good if we could actually find one with the motor effect thing actually being used. So let's try this one. That's in a different language now. There is an animation here. Here we are. Hungarian, English. Didn't do anything. Okay. I think it's translated other stuff, but the actual thing on the wire is still in Hungarian, apparently. So we've got a wire moved there, and what we could do with is, let's see if I can find a picture of Fleming's left-hand rule, how it looks. Okay, here you go. So Fleming's left-hand rule. So basically, your thumb represents the force, your forefinger represents the field, and the current, and your middle finger represents the current. So you point your left hand. It must be your left hand, like it's a gun, where your middle finger is like a trigger, and your forefinger is the tip of the gun, and then your thumb is whatever that how we generally use our fingers to pretend they're guns. Now, if you know that the symbol for magnetic field is B, this makes it a little bit easier because that would, as you go from thumb to forefinger to middle finger, it spells F for force, B for magnetic field, and I for the symbol for current, so FBI, and it looks like a gun. That makes it a little bit easier to remember. There are other ways to remember this. Some 1 mile physics teachers used to tell me that instead of thinking of thumb, think of thumb with an F, because it sounds silly, you're more likely to remember it. And yeah, anyway, so, but of course the trouble with that is field also begins with F, so there are different ways to remember this, but the main thing I want to focus on is how do we apply this. As long as you arrange your fingers and thumb in that way and remember which stands for which, then essentially you can maneuver your hand so as to work out the missing thing. So let's say you don't know what the force is, but you know the magnetic field is that direction, you know the current's that direction, then you can work out where the force is. So this thing over here shows that, and I don't know, let's see, we'll have to guess what these things mean. Yeah, that'll mean flipping the magnets around. Okay, and I'm not sure what this means. Oh, okay, right, so we see the size of the arrow, so that's changing the size of the, well, I is current, so changing the size of the current. This is changing the angle. This is going to be more applied to A level, although at GCSE you do need to know that if it was like that, then we have no resulting, or it says there's a force. Yeah, no resulting force there. That the force is going to be 0 there. There you go, it's down there. So really we should have it at 90 degrees. There we go. And yes, if you change the size of the current, you also change the size of the force as well. So that's more on Fleming's left-hand rule, otherwise known as the motor effect. There is a way of thinking about Fleming's left-hand rule in terms of combining the two magnetic fields, so the magnetic field around a wire and the magnetic field between the magnets. And I'll see if I can briefly show that before I run out of time on this video. Okay, great. So we've got the blue lines here represents the magnetic field of the bar magnet, and the black lines represents the magnetic field of the going around the wire. Now you can see above the wire, these fields would work together. They're both pointing from left to right, whereas below the wire, they're working against each other. So what happens is you get a resultant force like this one here. The ones above it become stronger, and the ones below it become weaker. So the sort of the resultant magnetic field is weaker below than it is above. And as a result, you get a resultant force pushing it down. So that's another way of thinking about the magnetic. So this is not using Fleming's left-hand rule, but it's still going to give you the same answer. If you were to apply Fleming's left-hand rule to this and not think about the magnetic field around the wire, then you will get the same answer. But this now helps you to understand it in terms of a combination of magnetic fields. Okay, let's go back. Let's see what else we've got down here. I would like to look at the difference between alternators and alternators and dynamos if I have time. Okay, great. I found a good question worksheet here. And I've given it 4 stars just because it's quite good, I think. I've opened it up just here. So these are questions all about alternators and dynamos. Sorry about the buzzer. 1 second. Right, so first of all, let's look at alternators then. So in fact, let's just look at it from briefly glance at it. We've got here a loop of wire, and this is first of all, we're spinning it deliberately. We're applying the spinning, so we're putting the movement in. Remember, we're generating electricity. We're putting the movement in, and we're getting electricity out. Now, the left hand of this wire is connected to this loop that's what you call a commutator. It's a slip ring, a slip ring. And that the slip ring that is furthest away from us. The slip ring here that is nearest to us is connected to this right-hand bit. As this rotates, anti-clockwise it looks like, then the right-hand one will appear on the left eventually, and the left one will appear on the right. But they'll both still be connected to the same slip rings as they were before. They're called slip rings because they're able to slip by this thing here, which is a graphite brush, and these brushes stay connected, so allow the electricity, the current, to pass along this, and while still not actually staying proper. The current is able to flow, but they're not physically connected, so as they're able to freely move while still maintaining contact. That's an alternator. Whereas let's look at, and it produces this alternating current. Let's look at this one, however. A dynamo is different. It has a split ring commutator. So now we've got the left-hand one. Again, this thing is free to move. The split ring commutator, similar to the slip rings, the split ring commutator. Here we go. Split ring commutator is able to freely move, and these graphite brushes will maintain contact while it's moving through until it comes to this split. So this is why it's called a split ring commutator, because the ring has been split. And when it gets to this split, and it passes over the brushes for a very small period of time, it doesn't maintain contact with the graphite brushes, and so or with the circuit, therefore, and so no electricity is being passed through at that point. Now, what that means is that this left side here, which is currently connected to the left part of this circuit, after a half turn, it will be connected to the right hand part of the circuit. After a quarter turn, if you imagine what's going to happen after a quarter turn, this split here that's going to be when it stops being connected to the circuit altogether. So once it goes from a half turn, then the left hand part of this then appears on the right hand side, and the right hand will appear on the left hand side. Now, using the motor effect, and using electromagnetic induction is going to produce a current pointing one direction. I'm going to run out of time to explain the details of the differences here, but essentially, I'll just have to say at this moment that the split allows for the sides to flip from one part of the circuit to the other side, and it maintains a positive current. So it looks like that, like I talked about earlier on. Whereas with the first case, with the alternator, it doesn't. They're always the left. This side here is always connected. I don't want to call it the left-hand side, because obviously at points in time it'll be the right-hand side. That will always be connected to this part of the brush. And that side will always be connected to this part of the brush, or this brush. So, and this produces an alternating current. So the alternator produces an alternating current, and the dynamo produces a direct current. So that's all I've got time for this video on loads of different things about magnetism at GCSE level and going into A level. Yeah, I hope that was helpful. Cheers. Bye.